You've probably seen tensile tests 100 times, but what about the compression test, especially for tricky materials like magnesium alloy? In the next few minutes, I'll show you exactly how to simulate a compression test in Abaqus step by step, from model setup and boundary conditions to interpreting the results. If you want to skip this tutorial and download the files directly, check out the pinned comment down below. Let's get started. Alright, as always, we start with part. Create part here. The part one is the cylinder, so 3D deformable solid extrusion, and this one must be 0.1, and we want to create a circle, so click on this one, create circle. First point must be here, and the second point must be on this axis, or here, here, or here. If you put the point somewhere around like here, when you want to mesh the model, you would have this part separated from this part and this part, so you would not have a good mesh. So I hit the Ctrl Z, and once more create the circle here, first point, and the second point must be here on one of these vertical or horizontal axes. So we select this one, add dimensions, and we select this circle 0.0065 and scroll button, done, and we have 0.016 and done. And as you see here, we have the cylinder. Okay, now it's time to create the sheet. It should be 3D, discrete rigid, shell, planar 0.1, and continue. We create a rectangle just like this, and we select the dimensions. It should be 0.02. This one also needs to be 0.02, and enter, done, and done here. Now we need to create a reference point. So from tools, reference point, we create a reference point just like here. So we created the cylinder and the sheet. So let's go to the materials properties, and here we create the materials properties. So from general, and density must be 1700 because it's a magnesium alloy. And from mechanical, elasticity and elastic, we select the Young's modulus at 44E9 and the Poisson's ratio of 0.3. And in terms of the mechanical plasticity and plastic, which is the flow stress, I have all these values here, so you can take a screenshot or you can comment down below asking for the materials properties. Okay, we jump back to Abaqus here and Control V, and as you see here we have the materials properties. What I like about this discrete rigid is that you don't need to assign materials properties to it. So we go to part one, and here we create a section. It should be solid, homogeneous, and continue. And we have material one, which is magnesium alloy, and then we assign the section. We select this one. I would like to uncheck this one in order not to create too many sets, and done, and okay. As it turns green, it means the section is assigned to it. As far as I'm concerned, we are finished with part, materials properties, and now it's time to go to assembly. Now here we need to assemble part 1, and we hold shift and select part 2. Okay, now we need to create another part 2. So this is part 1 and this is part 2, and I click OK. Now we have two part 2s. So we select on this one and OK. Now I can select, for instance, this one to be here, and I click OK for now. There's a very easy thing to do here is to go to query information, and we can find a point or node. So we select this one and we select done, and we have this coordinate here. Now if we want to move this one to the center, we know where to go. But there's an easier option. If you go to tools, and here from tools we can have datum, and you can intercoordinate or midway between 2 points. So I select this point and this point, and we have this datum point here. So we rotate it once more, holding Control and Alt, and we select this point and this point, and we have another datum point. So I click on here to reset the view. Now translate instance, select the instance first, and done. Now select this one, first point and second point, and done. Now we should do the same thing for the other one. Select instance first, done. This point should go here, and OK. And if you reset the view here, you have this assembly. OK, part is done, property is done, assembly is done, and it's time to go for step. Now we need to create a step here. Step must be dynamic explicit, so we find it here, dynamic explicit, and NLGeom must be on. And if we go to mass scaling, select this one, use the scaling definitions. So we create this one, semi-automatic, scale factor by 1600, and it should be whole model at the beginning of the step, and OK, then OK. Now we need to go to the interaction. OK, now we need to create contact. So the contact must be surface to surface contact explicit, and continue. We select this one, then done, and we select a surface, and we select this one, and OK, and it should be the purple here, and we need to switch this. We need the contact properties here, so it should be contact, continue, mechanical, tangential behavior, penalty, and the friction coefficient must be 0.3. OK, and we created one of the contacts, so this should be something like this. There's a contact between the two, and make sure this arrow points toward inside the cylinder. So we click on OK, and now we create another one, surface to surface contact. We select this one first, and done, and it should be, this time it must be brown, and we select surface, we select this one, and continue, and yes, it should be interaction property 1, and OK. And if we double click on this one, this arrow points toward inside the cylinder. So this is the interaction. Now interaction is done. So far we created part, property, assembly, step, interaction, and now we go to the most important part, which is the load. But before we start, I want to ask you a favor. If you enjoyed this video so far, please drop a comment down below. It's totally free for you, but it helps me a lot to grow. Thank you. Okay, pay attention here. We want to create the boundary condition. So here, create boundary condition, and from mechanical, symmetry, encast, I click continue, and I select this reference point, done, and I encast this part. So this part must be closed in every direction, so there is no degree of freedom, and this part is going to be displaced a little. So we create another one. Now this time we select displacement and rotation, continue, we select this one, done, and we select all of them here. But in U3 it should be minus 0.003, and it is not over yet. We need to create an amplitude because it is dynamic explicit. So if I don't click an amplitude, I would face an error, and as you see here, it says in an explicit analysis you need to create an amplitude, so it's a must. Click on this one, tabular, continue, and here we create a very simple amplitude, 0, 0, and 1, 1. Okay, and that's it for this one. Then we need to click on OK, but make sure to select it from here. So amplitude is selected, and that's it for load. So we have done everything, and we can go to the mesh. As in the assembly we selected part dependent, we cannot mesh that in the assembly, and as you see here it says dependent part cannot be edited here, so we have to select parts. We have part 1 and part 2. If not, we can go to assembly here, or from here we have the instances here. We have instance 1, 2, 3. We select them all and make them independent. So if we go to mesh to keep things simple, if I click on this one, it says select the parts to be meshed, and I click done, and as you see the parts are meshed. So yes, I want to keep things simple for now. This is a very bad mesh, but this video has only educational purposes, so I'm not focusing on this right now. So the mesh is created, and now we can go here and we create a job and continue, done, and we submit the job. We can monitor the job from here, and as you see there is no error, no anything, and it is being running. And right now the job is completed. Let's go and take a look at the results. We need to rotate this one, or we can choose it from here. We have top view, we have this is the side view, and as you see here the buckling is happening, so it's upside down. Maybe we can select this one, and as you see, yeah, this part is fixed and the top part is coming down, so the buckling happens. And here we can also modify that. We can stop wherever we want, and yeah, but this was just a stress contour. We can select different contours here. So this is the 1 mesos stress. We can have maximum principal stress, or we can have S22 here, as you see. And to see that better, let's go to option, comment, and here say feature edges. Yeah, this is better. We can also exaggerate a little by doubling this one. As you see here, the buckling can be exaggerated a little, but I don't want to do that right now. So this is what we have, and from here we can have in the contour option, we can go with auto compute and show location, and we apply this. We can have the location and the maximum value reported on this one here. Okay, let's see the displacement contour. Here we have U, and as you see here we have the maximum displacement on the top part. If you also want to capture a good image, you can go from viewport and viewport annotation option. You can set all off and only keep the legend, or maybe you can keep the triad just like this and click on OK. You can get rid of this maximum part, and that's also okay. So let's go to the viewport and annotation option once more, and in the legend you can set the font, or maybe you can bold the font here as you see, or you can change it if you want. This is okay, and we click on OK. Now this looks better, and if we put this one on maximum absolute principal stress, it looks better. We can have this one. If we want to compare that with an article or something like that, then we need to go to print here, and we select the file. So the file format can be PNG. Uncheck this one in order not to reduce down the color. So put the name like compression. I hope the spelling is right. This is the file name, but we should select this one, temp compression for instance, and okay, it should be the directory. Okay, and if we click on OK, we have the PNG image here created. And that's everything. Now that you learned the compression test, it's time to take things to the next level and learn the tensile test. Click on the video on screen before it ends, and I see you there.